Neural networks can be trained to reproduce the global illumination in a variable scene, but since each training sample is an expensive rendering, their number has to be limited. In this work we propose to encode a scene, with user-specified variables parameters, such as light and geometry positions, or materials, into a neural network. After training, we can render complex illumination effects, at interactive frame rates, while controlling all specified variable parameters. When the number of dimensions of the parameter space grows, training using uniformly distributed samples converges slowly and often fails at capturing complex effects as they become too sparsely distributed over the parameter space and are thus less likely to be observed. On the other hand, despite the recent advances in real-time path tracing, the low sample budget does not provide enough information to a denoiser to capture these effects either. We propose an active exploration method that guides sample generation to regions where they contribute most, and allows sample reuse to efficiently train a neural network to encode a complex variable scene, allowing interactive rendering over the full parameter space. Directly training our network with images rendered by uniformly sampling the variable parameters can treat some parts of light transport, as you can see from this video. Nonetheless, hard, important effects, such as reflections in the mirror, are poorly rendered in that case, even when training for a very long time. Indeed, the likelihood of covering hard, but important cases drops dramatically when uniformly sampling in high dimensions. For instance, observing the bottle on the table requires having the right combination of camera position and viewing direction, while observing the caustics also requires the right lighting conditions. In our active exploration method, we propose to guide the generation of training samples using MCMCs, allowing to explore these localized hard cases. Here, we visualize the position and scene configuration of patches that were selected by the MCMCs to generate training samples. Note that only the patch part in the red box was actually rendered during training. As you can see, the Markov chain first focuses on the mirror, then on other complex illumination configurations involving reflections or glass. At each training step, the scene configuration parameters are then concatenated to auxiliary G buffers that can easily be rasterized, such as normals, 3D positions or albedo, and given as input to a per-pixel neural network that generates the rendered image. At test time, the user is the one controlling the scene parameters. Here, the blinds, intensity of the ceiling light source, and the viewpoint can be controlled. We now show results in the form of recorded interactive sessions. The first scene was set up with 25 variable parameters. The user can control the color of the couches, the position of a group of objects, or even the light position. The second scene, containing 13 variable parameters, shows that our system can also be set up to control the presence of objects in the scene. Please note the color bleeding of the cylinder on the sphere when they get closer. Other result videos are presented in the supplemental webpage. Thank you for watching.